Hello, before I start the video, I just wanted to make a quick correction. In the tokenizer on line 99, there should be a break statement. It's just an error from first episode when we did the tokenizer. Without this, basically you get an issue where if you find the correct token, it will keep parsing and you may get sort of duplicate tokens or, yeah. So anyway, on with the video. Hello and welcome to the next episode of my compiler tutorial series. So in the last episode, we were starting off making the parser, and we managed to parse a struct. However, we still need to finish off the rest of the parser, and that sort of includes also parsing expressions, which is sort of an interesting subtopic. Right. So let's get started. So the first thing that I'd like to do is to start parsing procedures. So if it's an open parenthesis, we're going to make a procedure here. The procedure's name is equal to that name string. And now we want to parse the arguments of the procedure. So we're going to make a procedure to do that. I'm going to call it static node parse variadic. So this is going to be probably reused for some other things, but it's basically some sort of general form where we're iterating over elements. So if I bring up the graph file, if we just make an example in here, so we'll call it add, put that back, that add. So in the case like this, you can see that we have like declaration, comma, declaration, close parenthesis. So just any type of thing where we have sort of a start and an end thing, and then some sort of separators in between. So it's going to take parser. And it's also going to take the function with which we want to sort of parse each element with. So we're going to make an interface here. We call this parse function. And it's just going to be a node parser. So it's, yeah, just declaring this interface, then that lets us put that in there like that. So it's just so that yeah, we can sort of put different functions in here depending on what we want to do. So we're going to say token, or if parser.peakToken.type is not equal to open parenthesis, then we have an error. So print error variad must start with open parenthesis. Okay, otherwise parser eat token. Then while parser.peakToken.type is not equal to closing parenthesis. Right, we're going to yeah, so we're going to just iterate. So we're going to say node is equal to parse function. Whoops. Dot parser. So it's going to get something back, and then we're going to say if token or parser, sorry, .peakToken.type is not equal to comma, right? Then we break. Otherwise, parser.eToken. So if we encounter a comma, we keep going. Otherwise, we break out the loop. Then I'm going to say if parser.peakToken.type is not equal to closing parenthesis. So this is sort of the instance in which we have some sort of error. In fact, actually, right here, just as a fail-safe, we're going to parser.peak token is not equal to null, and that. So yeah, so we essentially want to just put in this. It should never really happen, but you know, the user may put in some invalid input, right? So in this sort of case, we can say print error variadic must end with close parenthesis like this. Otherwise, we eat that closing parenthesis and then we return. And this is going to be actually not a node, sorry, but a list of nodes. So list node parse variadic, and then in here we're going to define that list. I think we can just call it nodes, honestly. New array list. And then in here, we're going to just add it. So nodes, add node. And then we can return that, return nodes. Right. So we've done that. So the way that this is going to work is in our procedure parsing, we're going to say procedure.inputs is equal to parse variadic of the parser and parse statement. So this is essentially going to, it's going to, for each element, it's going to go back into here, and then hopefully if the user has written their program correctly, it's going to come down to this parse declaration thing and parse that out and then return. Okay, so procedure inputs, procedure.output is equal to, so actually first of all we want to check to see if they've defined a return. So you define a return with this forward arrow, but you can also omit it. So in the case of main, we don't have any sort of void type in our program, so if you don't want to have a return type, you just omit the forward arrow. So we want to check for that, so we're going to say if parser.peakToken.type is equal to forward arrow, right, then procedure.output is equal to parse type. So we're reusing that function that we used for the variable declaration. We actually want to say if, in fact, before we do this, we can say node type is this, and then we can just say if type is null, print an error. Procedures that define a return must have a return type. Must, I suppose, specify. Right, okay, so that will return out of that, otherwise we say procedure.output is equal to that type. Like that. Okay, then the last thing is actually the body. So the body is a bit more complicated because it requires that we have an expression sort of parsing system. So I'm going to discuss that now. So when we parse an expression, the basic format is it can either be a single leaf node. So what I mean by that is like for example the A or the B or a 2 or a whatever. So in an expression, in a long expression like this, the leaf nodes, or what we can call sub-expressions, are things like this, like the 2, the A, the B. It also actually includes things like procedure calls. So if we had another add in here like this of 2 and 3, that add would be a sub-node or sub-expression. So a procedure can either be just one of these things on its own, right? So we could just have return like, and this would be like a recursive thing, return add of 2 and 3, or it can be some sort of continuation, some sort of string of these subnodes, or sorry, sub-expressions separated by binary operators like this, like a plus or whatever. So before we start, we're going to just make the binary operator class. So binary operator implements node. It's going to have a public enum operation, and this is just going to find the different operations we have. So add, subtract, multiply, divide. Okay, it's going to have an instance of that enum, so public operation, public node left, public node right. Okay, and that's it. On top of that, we're just going to define a couple of different nodes for the different sub-expressions that we might have. So the first one is going to be called literal. So this is going to be a generic type that implements node, and it's just going to have a public t value, and for some ease of use when we're constructing this, we want a constructor. So this is going to store any sort of literal value. So what I mean by that is the 2, the 3, a 3.0, you know. So floats, ints, booleans, so like true, false, right? Not strings actually, because no, actually, so eventually we will have strings in this as well. However, we need to do some other work beforehand to get strings working. It's to do with the fact that strings are not a primitive. So even though you can define a string literal, so you can define like, you know, hello, the actual way that gets manipulated and stored is more like the way that a struct works under the hood. So it's a bit more complicated, and it's best to sort of postpone that to a later stage. So we've got the literal. We also want procedure call when we call procedures. It's going to have just a name and also a list of arguments or inputs. Okay. We also want a variable call. So this is just going to be when we reference a variable in an expression. So public string name is all we need. We could also define what variable it points to, but that's more for a later stage. And I think that's it actually. Yeah, so binary operators, literals, and variable calls and procedure calls. So now that we've got those, we can actually start by defining the sub-expression parsing. So the way that this is going to work is that essentially we're going to have a sort of high-level thing that parses the full expression, and that's going to parse individual sub-expressions. So we're just going to define that first. Put it here. So we'll say static node parse sub-expression parser. Oops. And I'm going to have a node or token start. It's equal to parser dot eat token actually. So I should have next in here. So next is this. If next dot type is equal to identifier. So in this case, it's either a variable call or a function call. Otherwise, if it's a number, then it's either a float or an integer. Otherwise, if it's a open parenthesis, then it's a bracketed expression. And otherwise, we're just going to return null for now. So it's just some unknown thing. We have an issue. Yeah. So in this case, we're going to say, first of all, we want to check if it's actually a float. So we want to say if parser.peakToken.type is equal to dot, then we want to make a float length variable. So this is just going to store in the source text how long our float is so that we can extract it. I'm going to first of all set this to the length of the next token. So that would be the sort of int token essentially. The first integer of this float. Then we're going to say if, once we've got that dot, we're going to eat that token actually, so parser eats token. Then we're going to say if parser.peakToken.type is equal to another integer, or it's a number, sorry, then we're going to increment the float length. Well, first of all, we're going to eat that token, so parser token decimal, I guess. Parser.eatToken, so we're going to eat that second number. We're going to say float length plus equals the decimal.length. And actually 1 plus that, because we're including the dot in this case. The first case, we don't want to, because as far as I understand, 2 dot does not parse correctly like in Java. So for example, float x equals 2 dot does not parse correctly. So if we pass in a string of 2 dot, it won't parse as correctly, whereas if we pass in 2, it will. And if we have a number afterwards, in fact, actually, we might need to parse this as double. We'll have a play around. We'll see what happens. We might have to put an F at the end. I'm not 100% sure. So, yeah. So that's fine. Now here we're going to say string float string is equal to program text, dot substring. So this is in the parser, sorry. So parser program text substring, and it's going to be next.index next.index plus the float length. And once we've got that, we're going to return a new literal. Return new literal. Yep. It's going to be float.parseFloat of that float string that we've constructed. Okay. Otherwise, if it's not a float, then we just return a new literal of integer parseInt of the parser dot the token value of that next token, so the first integer. Right, so we've done that. In the case where it's sorry, I've actually mixed these branches up. Sorry, so this is for the number. Yeah, okay. So for the first one, for the identifier, we want to check to see if the next token afterwards is open brace, in which case it's actually a function call. So if parser peakToken.type is equal to the open brace, or open parenthesis, sorry, then we want to parse an procedure call. Otherwise, we want to say variable call is equal to new variable call dot name is equal to get token value of the next token, and return that. Whereas in this case, we can say procedure call equals new procedure call. Procedure call dot name is equal to the token value of that next token, and we can say now procedure call dot inputs is equal to parse variadic of the parser, and also and in this case it's actually going to be parse expression. Unfortunately, we don't currently have that thing defined, so we're just going to sort of, in fact, actually we need it for open parenthesis as well. So in both of these cases, we're going to need to have the expression parsing. I think what we might do is just check this works. So we're just going to define some, or we're going to kind of just create something that only has variables and numbers in it, and then we're just going to see what happens. So it's not filled out yet, but yeah. So the next thing we actually want to do, just to get this to kind of work, is we want to define the return value, or the return statement, sorry. So in this, even if we have this sort of expression, we need to have this return defined. So let's define that now. So just below, if it's a keyword, we also want to check if it's a backwards arrow. So this is for return, right? We also want to make a node for that, so we want to make a new class called return statement. Implements node again, and it's just going to have a public node expression, I suppose. Or yes, right, so expression, or value maybe you could say. Similarly, you can just say return statement equals new return statement. We actually want to eat that backwards arrow, so we're going to say parser.eat token for that backwards arrow. And then in here, it's going to just be like statement.value equals parse expression. Okay, so now we sort of have to, we got all the groundwork set up so that we can write our expression parsing and test it. Okay, so to explain the different, or the reason why we will eventually code the expression parsing the way we do, I'm first just going to describe the problem of operator precedence. Then I'm going to describe sort of the two different ways that you can actually parse an expression, and then why the sort of it's the switching between these two different methods that actually allows us to properly parse an expression. So first of all, what's the problem? Okay, so the problem is that we've got something like a plus b times 2, right? Because of operator precedence, we want to parse this thing first and then parse the a afterwards, right? Because the multiply is higher precedence than the add. So whereas, right, so in this case, if we parsed iteratively, it wouldn't work, because if we would get something like a, right, then we'd retrieve the next thing of the expression. So if we went linearly left to right, we would get the wrong answer, because we would say a plus b multiplied by 2, right, and that'd be wrong. Whereas if we actually used our recursive method that we've been using so far, like with the rest of the compiler, we'd actually get the right answer. So if we recursively called parse expression, we get the right answer. We'd say a plus parse expression, right, b multiplied parse expression 2, and because 2, and then we would look ahead and we'd say, oh, there's no other binary operators, therefore we're just going to return early, right, out of this, and we get the right answer. Okay. But unfortunately, if this was in some other form, actually in the normal form, we'd get it wrong. So if we had a multiplied by b plus 2, this recursive method would give us the wrong answer, whereas the iterative method of like a multiplied by b plus 2 would give us the right answer. So it should maybe be kind of obvious now. So essentially, the recursive method gives us the right answer in the case where precedence is increasing. So in the case where we're going from a lower precedence like the plus to a higher precedence like the multiplier, and then the iterative method works when it's going down. Okay, so that's sort of the way that this works. So the way that works is that we interleave these two different methods, and it gives us the right answer. So we're going to go back to our code, and we're going to go to the just below where our parse expression is, the parse sub-expression. We're just going to define two methods, or two functions. One's going to be one's going to be static node parse increasing precedence. Okay, parser like before, but actually it's going to take in a node left, and it's going to take in a min precedence. Okay, then we're going to make another function called static node parse expression. It's also going to take in the parser, obviously, and it's going to take in just precedence, like this. For this case, we want to say, first of all, node left is equal to parse sub-expression, parser. Then we want to say while true, node right is equal to parse increasing precedence of our current precedence. And it's also going to include the parser and the left node that we've got here. We're going to say if left is equal to right. I'll explain this a bit more later, but we're going to break. Right. Otherwise, we're just going to say left is equal to right. Okay, so this might seem a bit confusing. We're going to return the left node. So this is sort of the iterative portion of it. But you can see we're calling out to the recursive method. Right, so in here, we're going to say if parser.peakToken.type is not equal to a binary operator. So actually we need to do a bit of work here. So we need to actually say, write a small helper expression for this. So public boolean is binary operator. Turn switch this, case plus true, default false, plus minus star / okay, true, default false, go back. If it's not a binary operator, then we want to just return left because the expression is ended. We also want to say if the precedence has dropped, then we want to also also in the case where the precedence has dropped, we want to return out. So to sort of figure out the precedence, first of all, what we actually want to do is we want to convert this token to a binary operator operation instead. So we're going to write another small function to do that. So it's going to be static binary operator operation to binary operation token. Right, and we're just going to return switch token.type case plus. It's going to be add, case minus, it's going to be subtract, case star, it's going to be multiply, and case forward slash is going to be, forward slash is going to be, type forward slash is going to be divide. In the default case, we're just going to return null, but it should never return null because we should have already just we should figure out that it's definitely a binary operator before we ever call this. Down here, we're going to say binary operator dot operation is equal to binary operation of parser dot peak token. If operation dot ordinal is less than or equal to the minimum precedence, which we're also going to return the left value. So it's essentially like an exit case here. Otherwise, we're going to make a new binary operator and we're going to say the operator dot operation is going to be equal to our operation. In fact, after this, we want to actually eat that token, so parser.eat token to eat the operator. And then in here, we're going to say binary operator.left is equal to the left, and the binary operator.right is equal to parse expression of the parser and the precedence of the current operator that we're on. So that's going to be the operation.ordinal. Okay, and we're just going to return that binary operator. Then we also just want to make another thing. So parse expression, parse, so static node parse expression, parser, and this is just going to return the parse expression of integer dot min value. Right. Okay, so so this should work. So now what we should be able to do is a few things. So in our return value, so return statement, we should be able to now say statement dot value is equal to parse expression. Okay, and return that statement. Also here, we want to say parse expression because this is the instance in which we are parsing a. This will be useful later. Actually, it's not critical here. Right. So just sort of double check our code. So we've got a plus b plus 2 times 3. Okay. We can get rid of this for now, just so that it's easier. And we're going to put a breakpoint here and then just see what happens, see if we get the correct answer or not. No, okay, so we've hit some sort of infinite loop. So just as a bit of a correction, there were 2 other errors. So the first one was that in our parse variadic function, this was peak token instead of eat token, which isn't correct. And then also when we did our procedure parsing, there was a few things. So the first thing was that once we'd found the forward arrow, we didn't actually eat the forward arrow, so that was an error. And then obviously the procedure wasn't filled out, so it needs to be like this. So procedure body equals parse block procedure to get the block statement, or the list of statements, and then obviously return the actual procedure, which is something silly that I forgot to mention. So now we're going to run again, see what happens. Right, so we get to the end here, and if we have a look at the program, you can see we have procedure, add, inputs A and B with the correct type, so ints. If we have a look at the output, it's type int. And if we have a look at the body, we have a return statement of a value of a binary operator of add of A and B and multiply of 2 and 3. So if you have a look at the value, again, this is correct. So we have the 2 and the 3, and then the add of the rest of everything. So yeah, so that's parsed that correctly, which is quite good. So I think we'll leave that for that there for now. In the next episode, I think probably what we might do just for a bit of fun is make a tree evaluator. So it's something that will take our syntax tree as it is and then just try and run that and have a play around and just see what we can get up to. Then I think after that we'll probably be sort of making it more correct and sorting out some of the holes and unfinished areas of the parser and that sort of thing, and fleshing out the language. So thanks very much for watching, and I hope to see you in the next episode.